Hello everyone, it's Dr. C. In the video today I would like to talk about empirical and molecular formulas. So what you should see in front of you is a representation of a molecule. This molecule happens to be called 1' 1 triple prime dimethylbiferracene, as you can see there. The name's not important. But this was a molecule that I synthesized in graduate school, one of the very first molecules that I made. And I make this molecule and I want to find out, did I indeed really make that? And this molecule wasn't a brand new molecule, it had been made before, but we were doing a different procedure that had a much higher yield. And so we had found a different way to make this compound, and we certainly wanted to find out, did we really make that? So University of Illinois, large research university, very well-supported chemistry program, and in the building across the street there was a microanalysis lab. And they would do what's called elemental analysis on your compounds. And so I wanted this compound contains carbon, hydrogen, and iron. So I took a sample across to the microanalysis lab in the morning, and by that afternoon I had the results. Pretty nice. And here are the results that I received back. 66.41% carbon, 5.54% hydrogen, and 28.05% iron. These are mass percentages, percents by mass. All right? So now we can use that information to calculate an empirical formula. So let's see how we do this. Now, I could actually start with the mass of sample that I took over to the laboratory to do this calculation. But we can choose an easier number. Since these are mass percents, what would be an easy number to choose? And I bet you came up with it. 100 grams. Okay? Because then these mass percentages convert directly to grams. But where are we going to go with this? Okay, we can get the grams of each substance, but what do we really need to calculate? And if you think about what subscripts in a formula mean, let's take a simple compound to start. Methane. We can read this as, in one molecule of methane, we have 1 carbon atom. We have 4 hydrogen atoms. But how else can we also read that? How can we read those subscripts? Yeah, we can actually say, well, let's say we have 1 mole of methane. In 1 mole of methane, Avogadro's number of molecules, how many moles of carbon will we have? Yeah, we will have 1 mole of carbon in 1 mole of methane, and we will have 4 moles of hydrogen. So there we go. That's the key. If we can get to moles, we can figure out the empirical formula of this compound. Do we know how to go from grams to moles? Yeah, sure we do. What conversion factor do we need? That's right, molar mass. So let's do this calculation. So by assuming 100 grams of substance, we have 66.41 grams of carbon, we have 5.54 grams of hydrogen, and we have 28.05 grams of iron. Okay, that's pretty straightforward. Now we're going to arrange our molar mass so that grams cancel and we end up with moles. So we want moles in the numerator, 1 mole of carbon, look on the periodic table, about 12.01 grams. 1 mole of hydrogen, about 1.008 grams of hydrogen, and 1 mole of iron is about 55.85 grams of iron. And you'll see that in each case grams cancel, leaving you moles of substance. All right, so what do we get here? For carbon, I get 5.530 moles of carbon. For hydrogen, 5.50. Okay, so I only carried 3 sig figs for hydrogen because that's all we had in the mass percent. And for iron, 0.5022 moles of iron. All right. So that is the mole ratio in which these elements combine to form this molecule, to form this compound. right? So we can write a formula from those numbers. It's not a formula that we would normally see, but this actually would be a correct representation of how they combine in terms of moles. All right? So that is a correct formula, but it's not the formula we want. What do we want those numbers to be as the subscripts? Yeah, we want them to be whole numbers, don't we? That's how we write formulas. So we need to get to whole numbers. All right, so what do we do at this point? Well, if you're thinking about it, if we divide by the smallest number, we're certainly going to get at least one whole number, right? So if I take 0.5022 divided by 0.5022, I have a whole number. I have a whole number of 1. That's nice. All right. Now, again, as we do a mathematical operation to keep this the same ratio between carbon, hydrogen, and iron, we have to divide each of those subscripts by the same number. Okay? And what does that get us to? Gets us to C11.01, hydrogen 11.0, and iron 1.000. Wow, that's pretty close to whole numbers. Now, there's going to be some experimental error in the process. This actually turned out really good, surprisingly good. Okay, so 11.01, we can round that to 11, hydrogen 11, and iron is 1. Okay, so this would be the empirical formula for that compound. Oops, sorry, I said compound and I meant formula. Empirical formula. There we go. All right, that's simple. So those mass percentages, if you assume 100 grams of substance, let's review really quickly, we can convert those directly to grams. We know how to convert grams to moles. The moles that you get is the correct mole ratio of how they combine, but we want whole numbers. Divide by the smallest number of moles, and quite often you will get whole numbers. Sometimes you won't, but you'll get really close. And then you should be able to figure out by what factor would you need to multiply to reach whole numbers. We'll do more like that in class. All right. So this does happen to be, let me scroll back up, the empirical formula of that molecule. Okay? So I know I'm on the right track, but I still need another piece of information to confirm that I actually made, well, I need more information, but another piece of information we're going to look at would help to confirm even more that I made that molecule. So let's take a look at an experimental technique here. And this is a schematic of a mass spectrometer. All right. So what we do with a mass spectrometer is the sample is going to be vaporized, get into the gas phase. Okay. You're going to have some type of ionizing beam, and various mass specs are different. This one is showing an electron beam, an electron impact mass spec. Okay. But what that beam does is, at a minimum, it's going to knock an electron off your sample. Okay? But you can also fragment the sample and break it into smaller pieces. Okay? So maybe a methyl group comes off, that CH3 group that was on the ring. Okay? So you can fragment the molecule. And the amount of fragmentation really depends on how strong the ionizing source is. So then we accelerate those ions, take them through a magnet here. Okay, so accelerating plates, get that beam, take it through a magnet. Now, those the parts of the molecule that come through are going to be charged species. Okay, so the least massive charged species, so say you break it into a small fragment like a methyl group CH3, those are going to be bent more. So the least massive ions are going to deflect the most in that magnetic field. The most massive ions will deflect less. Okay, charge to mass ratio or mass to charge ratio. Okay, so we can separate out these ions that come off of our sample. Okay, and one of the ions you're going to get is called the molecular ion peak. Okay, so you would have a spectrum and you'd have these different peaks that you would see for the different masses. So one peak is just going to be an electron is knocked off your molecule. So the mass that you're going to get is going to be the molecular mass. That's pretty cool. We're going to get other fragments, but in this case, we were most interested in seeing, well, what is the molecular mass of the compound? So I took a sample down to the mass spec facility, had them run a sample, and I got back the results, and the molecular ion peak of my sample was at 398 AMUs. Okay, so what do we do with that? Well, we know the empirical formula is C11H11Fe. Okay, this is the molecular mass, the mass of the molecular formula. Okay, we could also get a molar mass from that. We could say, right, this is 398 grams per mole of substance as well. So, what does that do for us? Well, what we can do is we can calculate the mass of the empirical formula. So let's get the empirical mass. All right, so let me see if I have a calculator here. I do. Hang on just a sec. So 11 carbons at 12.01, 11 hydrogens at 1.008, and iron is 55.85. Okay, let me just try that again. I'm not sure I quite got that right. Okay, so my empirical mass, I'm not going to carry too many sig figs here, but it comes out to 199 grams per mole. Okay, let's work with molar mass right now rather than molecular mass. All right, so the masses are different. What does that mean? Well, it means that our empirical and molecular formulas aren't the same. Okay, so if we take the molar mass divided by the empirical mass, okay, so the larger mass divided by the smaller mass, we can figure out how those two formulas are related. And I think you can see 398 grams divided by 199 grams, what do we get? We get a factor of 2. So if you work the problem correctly, you should get a whole number here, because the molecular formula is going to be some multiple of the empirical. It might be the same, so you would get a factor of 1. It might be double the empirical formula. In this case, we get a 2. If the molecular formula is triple the empirical formula, you would get a 3, and so on. So what that means is that our molecular formula is double the empirical formula. We double each of the subscripts. And so we end up with C22H22Fe2 for our molecular formula. That's pretty cool, huh? And turns out that if you went through this structure and you counted each of these vertices here as a carbon, okay, each of these carbons is going to have a hydrogen off of it. And if you want to take some time and draw them in, this carbon won't have a hydrogen because it's bonded over to another carbon. But you could go through and add your hydrogens on and count them up, and it is indeed C22H22Fe2. So I'm pretty confident at this point that I made the right compound. Pretty cool. Now, let me show you something really quick before I show you a different way we could solve this same problem. Because a lot of times, problem solving, if you can solve the same problem in multiple ways, then that really enhances your problem solving ability. So we'll do that. But we really wanted to make sure that we made this molecule. We wanted to figure out something about the structure too and see if there was anything interesting. So what we did at this point was the way this molecule is, it was very hard to make a single crystal of it unless we made a salt. Okay, so we made we had to have an anion to balance the cation. We this, and we made a salt that was called the triiodide salt of this. Okay, so what we did was actually make this molecule next. Okay, so this had a plus charge, and then triiodide has a -1. So we made a salt, and it was much easier than to crystallize that and grow a single crystal of that substance. And then we took it down to the basement of the building where there was an X-ray crystallography facility. We'll talk more about what X-ray crystallography is in class at some point this semester. But we can take that single crystal of the substance and use an X-ray source and all, computer modeling. It used to be they used to do it on, film. The X-rays would bounce off and you would see this repeating pattern and whatnot. But here is what the crystal structure came back as. Okay? And you can see all 4 rings. You can see a methyl group, that CH3 group there. So this was dimethyl biferrocene. There's the other methyl group there. Okay, here are the 2 iron centers. And wow, that really proves that we made the molecule. But the empirical and molecular formula together, we were pretty confident. So this is what's called an ORTEP diagram. And you get a lot more information than just this diagram. You get all the bond lengths, you get the bond angles, you get all this really cool stuff when you get this crystal structure done of your molecule. Really pretty neat. So now, let me just show you an alternative solution here. Okay, if we know the molar mass, 398, and the mass percent, okay, we can actually figure out how many grams of each element are in 1 mole of the compound. Remember, this is the mass per 1 mole of substance. So if I now take that, and let's look at the mass percentages again, just to refresh our memories. Let me scroll back up. 66.41%, 5.54%, and 28.05%. So if I actually kind of work this problem backwards, so I know it is 0.6641%. Now I've converted this to a fractional abundance, carbon, and take it times the molar mass, 398 grams. We can get the mass of carbon in 1 mole of that substance. Okay, 264.3 grams of carbon. All right, hydrogen was 5.54%, so 0.0554 for hydrogen, again times the molar mass. I'm going to carry an extra sig fig here, even though I only have 3. Try to avoid some rounding error. 0.05 grams of hydrogen. And then iron was 28.05%. So again, convert to a fraction. So 111.6 grams of iron. So if you added those up, you should get very close to 398. There's going to be some rounding errors in there, but it's going to be very close to 398. So in 1 mole of this substance, I have 264.3 grams carbon, 22 grams of hydrogen, 111.6 grams of iron. But remember, we want moles, right? We can read those subscripts as a mole ratio of how they combine. Do we know how to convert from grams to moles? Sure we do. 1 mole of carbon, 12.01 grams. 1 mole of hydrogen, 1.008 grams of hydrogen. And 1 mole of iron, 55.85 grams of iron. Let's see what we get. And I'm just going to, these come out very close to whole numbers. I get 22. This one's not as close, but that's, again, we rounded here a little bit. If you carried more sig figs in this number, you would get much closer to 22. Okay, so try doing that. Carry more sig figs for the grams of hydrogen and see what you get. And this comes out to almost 2. Okay, So since we started with the molar mass and used the mass percentages, these are the subscripts of the molecular formula. So my molecular formula, I can now get first. So again, we're kind of working this backwards. Rather than solving the empirical formula and then using the molar mass to get the molecular, we're using the molar mass and the percents to get the molecular formula, C22, H22, Fe2. All right? And then how do we get the empirical formula from that? Yeah, we just simplify the subscripts. Remember, the empirical formula is the simplest whole number ratio of how, in this case, carbon, hydrogen, and iron combine. So what can we do? Yeah, divide each of those subscripts by 2, and we end up with C11, H11, Fe. That's the simplest whole number ratio of how those combine. That is our empirical formula. Okay? So solving problems, it really helps your ability if you can solve the same problem in different methods. Okay? And again, just to highlight, the first way we did it, we used mass percent data to get the empirical formula. Then we brought in the molar mass or molecular mass to go from empirical to molecular. Make sure you know how to do that. Okay? Because some problems you might get, it might just say calculate an empirical formula. It might not have you go to the molecular formula. But if it wants you to calculate the molecular as well, you will either measure in the laboratory like I did, where I use mass spec to get the molecular mass or the molar mass. But in a problem in class, I would give you the molar mass of the compound. If that's given, you could work this other way, where you take the molar mass and the mass percent to actually calculate the molecular formula first, and then you just simplify that molecular formula to get the empirical. All right. I hope this makes sense. Please let me know if you have any questions, and we will work another example of this in class just to make sure we're all on the same page. So I will see you very soon. All right, take care.